So the next presentation is Efficient Semantic Scene Completion Network with Spatial Group Convolution. The authors are Jiahui, Zhang, Zhao, Anbang, Liao, Yurong, Chen, Zhang, and Hongen, Liao. Sorry for the pronunciation. And Jiahui is presenting.
So, good afternoon, everyone. I'm Jiahui from Tsinghua University. Here we will present a work which is maybe much easier to understand. So, our work is Efficient Semantic Scene Completion Network with Spatial Group Convolution. 3D data analyzing and synthesizing has attracted increased attention recently because of its wide range of applications such as robotics, autonomous driving, and so on. Since convolutional network has achieved great success in 2D areas, extending scene to 3D data should be a promising direction. However, it is not a trivial task to adopt 3D scene by just adding one dimension to 2D scene. The difficulty lies in the cubic growth of computation and memory requirements of dense 3D scene. So, improving the efficiency of 3D scene has been a long-standing goal over the last few years, and we attempt to achieve this goal by making full use of sparsity of 3D data. Our work is inspired by several characteristics of 3D data. Firstly, intrinsic sparsity of 3D data. Most of the voxels in 3D data are empty. Non-trivial voxels usually exist near the boundary of objects. This property has been exploited in several recent works such as ArcNet, OCN, and SCN. We adopt previous sparse convolutional network to exploit the intrinsic sparsity of 3D data to avoid unnecessary memory and computation on empty voxels. However, the computation is still intensive when the resolution is high or the input is not so sparse. For example, the complexity of SCN used in our paper is about 80 flops, while only outputting 1 in 64 size predictions. So, we propose to use the second characteristic of 3D data to further reduce the computation, which is the redundancy of 3D data. As shown in the figure, discarding a large portion of voxels randomly does not prevent humans from reasoning the overall semantic information. More specifically, we build our work on SCN and step further by encouraging higher sparsity in feature maps. We partition features into different groups and conduct sparse convolutional network on each group. The computation can be largely reduced thanks to the characteristics of SCN. Thirdly, we notice there exists complementary information among different groups after partitioning, giving only partial voxels makes it hard to recognize small and thin objects. So, in order to utilize the complementary information, results of different groups are gathered for further processing. We call the operation containing the designs a spatial group convolution. The pipeline of spatial group convolution is as follows. We first partition features into different groups, and then apply sparse convolution network on each group. Features of different groups are gathered in the middle of the network. We will give more details about the designs, such as the partition strategies and new sparse convolutional network architecture. Previous work about the efficient network design in 2D area usually exploit group convolution, such as mobile nets and shelf nets, while in 3D area, we speed up networks from another perspective by encouraging higher sparsity in features. Our SGC is orthogonal to group convolution. It is defined on spatial dimension, while group convolution is defined on channel dimension. Besides, in SGC, we are shared between different groups because voxels in different groups are similar. Here we first introduce the partition strategy, which exploits redundancy of 3D data. We present two different partition methods. First, random partition method. Voxels are partitioned into different groups randomly and uniformly. This partition method expects convolutional features to be invariant to all possible activation patterns, which may be hard for CN to learn. So we propose the second method. We partition voxels into a fixed pattern for all samples. More specifically, we partition voxels according to the voxel's position. The group index is determined by the following formulation. Different variable A, B, C, and G can give different patterns. We also exploit more complicated partition methods to help information flow among different groups, such as shuffled SGC, which is inspired by ShuffleNet. We shuffle the features across spatial dimensions, but no obvious improvement is observed in our case. So here, we mainly report the results of these two previous methods. Next, we use previous sparse convolutional network to exploit the intrinsic sparsity of 3D data. SCN uses hash table to store non-empty voxels in 3D feature. Non-active sites with the red in the figure have no computation overhead or memory overhead. Besides, because dense convolution will cause structure dilation problem and soon destroy the sparsity of features, SCN forces to keep sparsity at the same level throughout the network, which means that active sites are unchanged during sparse convolution. These designs can largely decrease computation and memory requirements, enabling the usage of deeper 3D CNN. So, why SGC can reduce the computation overhead of SCN? The key is that we found a match between spatial group convolution and sparse convolution. As shown in the figure, the computation overhead of sparse convolution is related to the sparsity of voxels. Since SGC makes voxels sparser by partitioning, the final computation overhead is about 1 ng of original computation. As shown in the figure, computation is reduced from 8 plus 6 to 4 plus 4. Finally, we gather information of different groups in SGC. Note that operation only occurs when the resolution changes. We will give more details about the network design. Since we expect our SGC to be a generic operation, we choose semantic scene completion as our application because of its two characteristics. Inputting a depth image, SSC not only aims to predict dense labels, but also aims to output a complete shape which is different from the input. These two characteristics make SSC a typical 3D dense prediction task, which can represent segmentation, completion, RGB diffusion, and so on. However, previous SCN could not be directly used for completion tasks because active sites are unchanged during SCN. No new voxels are generated for completion. We will introduce a novel sparse convolutional network to predict unknown structures. The key for completion are the introduction of dense deconvolution module and abstracting module. We use multi-scale encoder-decoder architecture as shown in the figure. Encoder module is constituted of sparse convolutions described before. While in decoder module, we implement a dense deconvolution layer to generate new voxels. More specifically, after a dense upsampling deconvolution layer, each voxels in low resolution will generate 8 voxels in high resolution. New voxels can be generated from this process. Applying dense deconvolution module repeatedly can generate all missing structures, but it will soon destroy the sparsity of 3D feature maps. So we introduce abstracting module similar to OctFusion, which predict a cost structure and removes unnecessary voxels in low resolution according to the prediction. Only valid voxels and boundaries are passed into higher resolution. Here we show the results of our network on SunCG dataset, which is a large-scale synthetic scene dataset. We outperform previous SSCNet by a significant margin, having an improvement of 24% in semantic scene completion and 11% in scene completion. achieving state-of-the-art results. Our network exceeds SSNet in almost all classes. We attribute the improvement to our network design, which enables building much deeper networks. The drop in recall is due to the sparse representation of geometry. There are some visualization results. Obviously, our network produces better results compared to previous work, such as the object boundaries in the figure above and TVs and chairs in the figure below. Here are more results. Okay. This slide shows the results of network after applying SGC. Overall, SGC can significantly reduce computation while maintaining accuracy. As shown in the left figure, the reduced flops are nearly linear to the group number, which is consistent with our analysis. We achieve about 1% IOU drop while using only 1/4 computation. As shown in the right figure, compared to random partition method, fixed pattern partition method gives better performance, yet requires less computation. We analyze the influence of SGC on each category. These negative numbers mean accuracy drop. It can be found that accuracies of categories with small physical size drops more than categories with large size, such as ceiling, floor, and wall, which is reasonable considering dividing small objects into different groups loses more important information. We also conduct experiments on noisy real-world NYU dataset. Experiments show that both our network design and SGC operation are still effective on real-world data. Next, we will give more discussions about SGC. One of the important questions about SGC is what does SGC learn? We visualize the histograms of learned width of SGC with random partition method. The histograms become sharper with the increase of group number. This may be caused by that filters of SGC need to be invariant to be different sparsity patterns. So the values of filters at different locations had better to be closed to adapt to different sparsity patterns. As for SGC with fixed pattern partition, we find it learns an irregular convolutional kernel. In the left figure, we show a simple case in 2D convolution, which divides voxels into two groups. The valid convolution kernel shape is always X because the sparsity pattern keeps the same when sliding the convolutional kernel. The right figure shows the irregular valid filter shapes learned in our experiments. The filters are drawn by slice. At last, we summarize our main contributions here. We propose SGC by exploiting sparsity of features, which can significantly reduce computation with slight loss of accuracy. We present a novel end-to-end sparse convolutional network design for 3D semantic scene completion. And finally, we achieve state-of-the-art results. So thank you. Thank you for your listening.
Thank you. Are there questions? Okay, so what happens if you have small details which are important, small details in your 3D points which are important for the recognition? Are you going to miss these small details because of the subsampling?
You mean the accuracy? You mean the accuracy drops much than the of the small objects? Mm-hmm. Okay, this might be caused by that small objects has little voxels and we have divided the small objects into several groups. So in each group, the geometry information may lose much more than the objects with high size with large size. Mm-hmm. Okay. Okay.
So did you compare with only one subsampling, where so instead of using only the 3D points, you could use also the normals or the curvatures, computing from all the points, so from the initial 3D points. So instead of using the points, you could use also more geometric features, the normals, the
you mean we can use normals to as input?
To compensate for the fact that you do a subsampling.
Okay. Well, actually, we have not tried this method, but we think it might be an interesting suggestions.
Okay. Any questions? No? Okay. So then let's thank the speaker again. Thank you.
Thank you.